Welcome to Teja Statistics. In this class, we are going to discuss some problems on probability. One card is drawn from a regular deck of 52 cards. What is the probability that a card is being either red or a king? So, solution for this, uh, let S be the sample space for drawing a card. So, N of S is equals to 52 C1, that is 52. Let A be the an event of drawing a red card. So how many red cards are going to be exist? Because there are 26. Okay, 26 cards. So from that we have to draw at least one. Sorry, exactly one. So let A be the an event of drawing a red card. So 26 C1. Let B be the an event of drawing a king. N of B, that is 4C1. So kings are B 4 cards. Okay, so 4C1. So probability of A is equals to N of A divided by N of S, that is 26 divided by 52. Probability of B is equals to N of B divided by N of S, that is 4 divided by 52. Probability of uh, A intersection B, N of A intersection B divided by N of S. So how many red cards of kings will be there? Okay, in a deck of cards. So there are uh, 4 kings. They are from 2 red cards. Okay, so there should be 2 red cards. So that is what the intersection of both they are 2 divided by 52. By addition theorem of the probability of A union B is equals to P of A plus P of B minus P of A intersection B. So that is 26 divided by 52 plus 4 divided by 52 minus 2 divided by 52. That is probability of A plus probability of B minus probability of A intersection B. So probability of A union B will gives you 28 divided by 52. So in cancellation you got 7 divided by 13. Okay, next question. A box contains 20 tickets numbered from 1 to 20. A ticket is drawn at random. Find the probability that it is divisible by 3 or 4. So 3 or 4. So you have to be very careful while doing these R problems. So total number of tickets are 20. The total number of outcomes, so you're drawing at least exactly one ticket from that. So that is not at least, it is exactly. So how many ways you can do that? 20 C1. So 20 C1 is your outcomes. Let A be an event that the number is divisible by 3. So what are the possible cases for this divisible by 3? That is 3, 6, 9, 12, 15, 18. So how many number of cases are there? 6. So total probability, that is 6 divided by 20. Okay, next let E be the numbered that is divisible by 4. So what are the possible cases for this? 4, 8, 12, 16, 20. So N of B is equals to 5. So A intersection B, the number which is divisible by 3 or 4. The only common point in this both favorable events, that is 12. So there exists only one case, so that is 12. N of A intersection B is 1. Therefore, the probability of A intersection B is equals to N of A intersection B divided by N of S, that is 1 divided by 20. Okay, so this will be 1 divided by 20. By the addition theorem of the probability of A union B is equals to P of A plus P of B minus P of A intersection B. That is 6 divided by 20 plus 5 divided by 20 minus 1 divided by 20. Totally we got 10 divided by 20, that is 1 by 2. There is 50% of chance. Yes. One more question here. A bag contains 4 green balls and 6 black balls and 7 green and white balls. A ball is drawn at random. What is the probability that it is either a green or a black? So what are that? Let's see. So total number of balls are 6 plus 4 plus 7, that is 17. From that you are drawing at least exactly one. So if n equals to, that is 17c1, so let A be the an event of drawing a green ball. So n of A is equals to 4c1, that is 4. Probability of A is equals to n of A divided by n of S, that is 4 divided by 17. Let B be the an event of drawing a black ball, that is n of B is equals to 6c1, because there are 6 black balls. So probability of B is equals to n of B divided by n of S, that is 6 divided by 17. So A intersection B is equals to 5. No common elements between the two events A and B, that is 0. So probability of A union B is equals to P of A plus P of B minus P of A intersection B, that is 6 plus 4, 10 divided by 17. Okay, directly you will get the answer also. Yes, this is the probability of getting a green or a black ball. Yes, one more question. A card is drawn from a pack of cards. What is the probability that it is either a black card or it is an ace? You can see that you are deriving or drawing a card from the pack of cards which is containing 52. So 52c1, that is 52 is your n out of values, that is outcomes. Next, let A be the event that is drawing a black card. So how many black cards are going to be there? 26, 26c1, that is 26. Next, probability of A is equals to 26 divided by 52. Let B be the drawing an ace card. So how many ace cards will be there? 4c1, that is next. In continuation, by the addition theorem of probability, we have the black card, that is how many black cards are there in the ace, that is A intersection B, that is 2 cards, that is okay, so 2 divided by 52, that is the intersection value. By the addition theorem of probability, P of A plus P of B minus P of A intersection B we got, that is finally we got 28 divided by 52, that is 7 divided by 13 again. Yes. Next, addition theorem of the probability. Yes, for any events. Okay, the probability of union I runs from 1 to n of ai summation I runs from 1 to n of p of ai minus double summation. So p of ai intersection ej, that is plus triple summation 1 less than I less than or equals to j less than or equals to k less than or equals to n, and so on, minus 1 whole to the power of n minus 1, p of a1 intersection a2 intersection and so on intersection an. This theorem can be proved by the principle of mathematical induction. For n equals to 2, you have to substitute p of a1 union a2 is equals to p of a1 plus p of a2 minus p of a1 intersection a2. So this is from the addition theorem of the probability we got, hence it is proved for n equals to 2. Next, let us suppose that this theorem is true for n equals to r. So p of I equals to 1 to r of ai, so you will get the values I equals to 1 to r of p of ai summation, and also put as equation 2. So now we have to show that it is also be true for n equals to r plus 1. So let's see that n equals to r plus 1 statement you have to consider from the 1. So this is divided into the two parts, I equals to 1 to r and union a of r plus 1 you are adding. So from 1 this is in the form of a1 union a2, a1 union a2, hence it is uh, expanded for by the addition theorem of probability for two events. So next we have to substitute the complete n equals to r statement over here, and from 2 we got the equation like this. Then after to add each and every term with the ar plus 1, hence this complete statement is also be true for n equals to r plus 1. So by the mathematical induction we can prove this theorem. Okay, next coming to the Boole's inequality. So what is a Boole's inequality? For any events a1 a2 a3 and so on and we have the theorems statements given by the Boole's. So very important, and we can prove this theorem by the principle of mathematical induction once again. For n equals to 2 you have to substitute n equals to 2 a1 plus a2 minus p of a1 intersection a2 less than or equals to 1. So that implies a1 intersection a2 greater than or equals to p of a1 plus p of a2 minus 1. If you move this one in the value of the statements, then you will get that is 2 minus 1, hence this statement is true for n equals to 2. Let us suppose the given result is also be true for n equals to r events, then n equals to r we have the theorems, that is p of I equals to 1 to r of ai greater than or equals to summation I equals to 1 to r p of ai minus r minus 1, put as equation number 2. Now we have to show that this also be true for n equals to r plus 1. So from that you can split this complete statement up to two terms, that is I equals to 1 to r of intersection of ar plus 1. So from 1 we can write that it is extended up to p of I equals to 1 to r of ai plus p of ar plus 1 minus 1. So from 2 this can be expanded up to ar plus 1 and minus r plus 1 minus 1. So plus minus 1 gets cancelled and this will be our statement. Okay, that is this complete result is true for n equals to r plus 1 also. we can prove the second statement by the principle of mathematics, mathematical induction again. So for 2 events a1 and a2, we have the values like this. Then p of a1 intersection a2 is equals to p of a1 plus p of a2 minus p of a1 uh, uh, intersection a2 is always greater than or equals to 0. Yes, this value is moved to the right hand side, then you will get p of a1 union a2 is always less than or equals to p of a1 plus p of a2. The put as equation number 1. So summation will remain same. This the result is true for n equals to 2. Let us suppose that the result is also be true for n equals to r. Now this is our statement. Now we have to prove that it is also be true for n equals to r plus 1. So from 1 left hand side we are expanding that I equals to 1 to r plus 1, and we are splitting into the two equations I equals to 1 to r of ai union r plus a1. From 1 it is less than or equals to value, and this is up to this. Okay, hence this result is also be true for n equals to r plus 1. By the principle of mathematical induction, the result is also be true for n equals to r plus 1. Thank you.